Alright, so today we're going to talk about vectors once again. We're going to look at a couple more properties of vectors and what we can do with them. So I want to start off by pointing out that we can find a vector between 2 points. A vector doesn't just have to exist from the origin. So let's imagine we have 2 points in space, in three-dimensional points, A and B. There exists a vector AB that can be defined as sort of a line almost, but really it's not quite a line because it has that direction from A to B. So how we can find this is we need the vector from the origin, or the direction vector, of A and B, and we're going to take the difference of these two vectors. So as an example, let's give ourselves a point for A. Let's say that A is at 5, 6, and 2, and then B is at 10, 3, and try that again, 3 and -4. Alright, I know the handwriting's not so great, but I'll try and write a little bit bigger. So the vector AB then is going to be equal to whatever B1 minus A1 is, and then B2 minus A2, and then B3 minus A3. Now again, we don't have to write this in column form, we could also write this in the base form as well. That's just where you're going to make it look like a sum of 3 values. Okay, so let's formalize this. We could do 10 minus 5 is 5. 3 minus 6 is -3. And then -4 minus 2 is -6. So this would be our vector that we've drawn here from A to B. Like any other vector, we can find the magnitude of this one, and that is just by taking the square root of the of the sum of the squares of each of these values. So if we want to find, say, the magnitude of AB, we can plug it into this formula here. 5 squared plus, and I'm just going to write 3 squared because we know that negatives in this case don't matter since they're squared, and 6 squared. What we end up with, 25, 9, and 36. A little bit of mental math. That's going to be, what, 70? Square root of 70. Cool. We are. A from B to get the vector AB. So this brings us to things that we need to be aware that we can do with vectors. So we can actually add vectors, and I haven't shown an example of that yet, but if we add two vectors, let's say we have this vector and this vector from the origin there, we can add them to get perhaps a vector that looks a little bit like this as well. How that works? Well, if we have a vector v and a vector w, well, v plus w is just adding up the individual parts. So similarly to what I wrote on the last slide, we just have v1 plus w1, v2 plus w2, and v3 plus w3. Okay. All right. We can subtract them. This is what we saw in the last slide with subtracting. We can multiply them. So this is an interesting sort of new idea. This is called the scalar product. And the reason why we call it the scalar product is it can actually be done 2 different ways. So when we multiply them, we can multiply them in a way that you might expect. Let's say we have v and w again. A scalar product can be written as v times w, oops, that's 2 w's. V times w is equal to what we might expect, V1 times W1, V2 times W2, and V3 times W3. But this can also be written as the product of the magnitudes times, and this is important here, the cosine of theta. If I can just write this, the cosine of theta. You might be like, well, where's theta? What is theta here? Yeah, theta is an angle, but what is the angle of these two vectors? So this gets at the next part here, which is finding the angle between the two vectors. And yes, there is an angle. There's always an angle between two vectors in space. And you might think, well, what if they're in vastly different areas? That's true. They could be all over the place. But any two vectors, this vector and this vector over here, they have an angle between them. You can reposition them. Let's see if I can do that here. Oh no, that's my drawings. Never mind. Yeah, you can reposition them so that your first vector or your second vector crosses the other. Now, you might think, well, the values of them will change. Well, not really, unless you're just talking about it always coming from the origin. It still has the same magnitude in the same direction, therefore it's the same vector. So I've literally sort of just copied that vector from over there. And now it does indeed have an angle here, that theta. Okay, so why is that angle important? Well, for the next thing here, we can determine parallel or perpendicular vectors. This can be really important in some applications, seeing if different forces are acting, say, together or in opposition with each other. So let's look at some examples. Alright, here I have two vectors, and they're given to you with column form, A and B. And what we're going to do with these vectors is we're going to multiply them. We're going to find the scalar product. So scalar product, again, A times B, can be written as A1 times B1, A2 times B2, and A3 times B3. But we want to find, say, the angle between our vectors here. And what we need to do is then compare this result with our result of the magnitude of A times the magnitude of B times cosine of theta. Now, one thing you might be noticing right now is that this second value here should be just one value, yet this one we've got three different values. Well, we're going to stop using column form to find our actual scalar product, because in base form, this column form is actually just the sum of the three values. So we're going to be comparing the sum of the three values to this value A times B cosine theta. Alright, so I've gone ahead and done a little bit of the work here, just written out our product. So we've got 15 plus negative 12. Okay, there we go. Not quite. Plus 12. So that just equals 15. And so we can set up an equation here that 15 equals the magnitude of A times the magnitude of B times cosine of theta. Alright, so I also went ahead and found the magnitudes of A and B respectively. That's square root of 61 and square root of 38. So now we finally can set up this last equation here for theta. and it's going to be equal to the inverse cosine of our 15 divided by the product of our two magnitudes. So 15 divided by the square root of 61 times the square root of 38. We're definitely going to need a calculator for this, but one moment. Alright, after consulting the calculator here, we have that the answer here, I'm going to put it right down to the bottom, in radians is 1.25, and in degrees, we can convert that to degrees, it's 71.85 degrees. Okay, a little sloppy. Some things to note here. So, our result was that the angle, 71.85 degrees, was acute, less than 90 degrees. And one thing that you might recognize about, say, cosines and the unit circle is cosine is going to be positive whenever you have an angle between 0 and 90. But if you have an angle between 90 and 180, then your cosine is going to be negative. And really, those are the only angles we're going to be concerned with as an angle between two vectors. So how do you tell if your angle between two vectors is obtuse, which is greater than 90, or acute, which is less than 90? Well, it's going to depend on whether or not your scalar product is negative or positive.